Number of moles is unknown. We don't know it. What is the number of moles here, right? And the question is, if you have a volume of 1 quark, if you have a density of this much, right? How many moles are there? Okay, so how many moles are there if you have volume and density? Now, sometimes we have to use our intuition. Intuition is sometimes if volume is given, density is given, what is the purpose of having volume and density? Find the mass. You see, find the mass. Because there is a reason for us here, volume is given and density is given, and we know from the relationship of density, density is mass over volume, right? Density is mass over volume. This implies that mass equals to density times volume. Mass equals to density times volume, right? So, in order for me to know the number of moles, I need to know the molar mass. I need to know the mass. That's the relationship between moles and mass. Okay. Now, from this information, I can calculate mass of the alcohol here. But I have also one problem because density is given in gram per milliliter. Volume is given in quarts, right? They don't compatible. They are not compatible. They are not matching each other. So I have to make some change here, and I know that somewhere here, because I have all my known values, it is given to me 1 quart equals 946 milliliters. This was given to me, right? 1 quart equals 946 milliliters. So basically, the quart is the same as what? 946 milliliters. 946 milliliters. So the mass will be the density, which is here, and the volume, which is here, and the unknown, I mean the milliliters, because we're not looking for milliliters, we're looking for mass, they will be eliminated here. Okay, so the mass will be, we multiply 0.785 by 946. Okay. When we multiply this, what do we get? 742.61 grams, right? Yes. And also, we have to apply our knowledge of significant figures, right? When you multiply numbers, we always do 3 significant figures. So you have 5 significant figures here, 742.61. There are 5. So we have to eliminate this into what? Into 3 significant figures, right? So we can say this is approximately 743 grams. Okay? But this is mass. This is mass. This is not the final answer. Okay? So the final answer is we're looking for what? The number of moles in 743 grams. The number of moles in 743 grams. So I'm continuing this. And I'll say 1 mole of C2H5OH by the definition equals to how many grams?
46.
1 mole of C2H5OH equals to how many grams?
46.
46. How did we get that? The weight of carbon by 2, the weight of hydrogen by 5, the weight of oxygen by 16, the atomic weight of each element, and also the weight of hydrogen, because we have hydrogen here. So if you add all this up, you will get 46 grams. That's 1 mole. That's 1 mole, right? If 1 mole has 46 grams, then the next step would be, if I have 743 grams of C2H5OH, how many moles I would get in 743 grams? Yes, we use conversion factors. See, conversion factors. So we're going to put 1 mole over 46 grams. And remember that always the required unit, the desired unit, has to be on the top. What I'm looking for has to be on the top. The unwanted unit has to be on the bottom, because I'm looking for mole. Here I have mass. Mass was given, and my destination is what? I mean, I have mole. My destination is, oh wait a minute. I have mass. My destination is mole. This is my destination. I have mass. The mass is here, 743, and I'm looking for mole. Okay. So, you know, grams and grams will be denominated in 743 times 1 over 46. 16.1. 16?
16.2.
Which one?
16.2.
16.2. 16.2 more. If you divide that, you get 16.2. Any question you have? Questions? Okay. Now, let's make some more practices regarding later with this. I have other problems as well.
Professor, can I
If you have any questions in the meantime regarding with this,
Okay.
you done? Okay. Okay. Okay, this is a practice exercise that I want all of us trying to do it first, okay? Let's try this problem and then we go from there. The masses of diamonds and other gemstones, precious materials, are measured in carats. Like gold has 15 carats, 18 carats, 21 carats. And there are exactly 5 carats per gram. There are exactly 5 carats per gram. That means 1 gram has 5 carats. 1 gram has 5 carats. Now, the question is, how many moles of carbon atoms are in 0.55 carats diamond? Okay. And the other question is, how many carbon atoms are in 0.55 carats diamond? Then these are following up. It's a follow-up questions. And then, okay, let's first do this. Let's first do this part here. Okay, let's try to solve this problem, and then we go from the next. Okay, because this is the second problem. Calculate the mass in kilograms of 219.9 moles of boron. That's a different question. Okay. Now, I'll give you like 5 minutes or 10 minutes maybe. How you solve this problem? How do you apply between mole of a substance and mass of substance? We know that 1 mole of carbon equals to how many grams of carbon? 12. 1 mole of carbon is 12 grams. 1 mole of sodium equals to 26 grams of sodium. 1 mole of water equals to 18 grams. So always there is a relationship between mole and mass. There is always a relationship. There is no any relationship between moles and carats. We never heard that. But we know the fact that we can change the carats to grams. We can change that. It says here, it says here that there is 5 carats per gram. What does that mean? 1 gram has 5 carats. 1 gram has 5 carats. Okay. So if I have 0.55 carats, 0.55 carats diamond, how many grams I have?
2.75.
I'm sorry?
2.75.
2.75. How did you get that?
Multiply
5.
Okay.
I did not do it. I want to 0.55 times.
Say it one more time. 1 mole has how many carbons in it?
We have 0.55 carats, right? It's given to us, right? And it says that 1 gram has 5 carats. Right? That's what it says. That 1 gram has 5 carats. Then if I have, in how many grams I have in 0.55 carats? I do convergence. Whenever I do convergence, always, what is the principle? What's the basic principle? the known value has to be written on the top, which is 1 gram over 5 carats. And carats will become 0.55 times 1 divided by 5 is going to be 0.11 grams. 0.11 grams. Okay? But this is grams. This is grams. But the question is, how many moles of carbon atoms are there? So, I'm going to apply molar mass, the theory of molar mass. Molar mass always 1 mole of a substance equals to the atomic weight of substance in grams. Okay, final carbon, the atomic weight of carbon is 12, right? So 1 mole of carbon equals to 12 grams. That's the definition. 1 mole of carbon equals to 12
Where
grams.
did you get that? One more is carbon is low.
Where do I get that? That's the question. Where do I get 1 mole of carbon equals 12 grams? Periodic table, right?
So it's like all the numbers here, like
Yes,
or,
yes.
or like 1 mole.
Yes. Well, now all the numbers that are there are listed in terms of atomic mass unit. Atomic mass units. That's why that's the difference between atomic weight and molar mass. But take that number and convert that in grams, and that makes sure that the substance that you have is about 1 mole.
So this is sort of like atomic weight for this element.
Yes, numerically they are equal. The atomic weight and the molar mass numerically they are equal. But the difference is that the atomic weight is written in AMU. The molar mass is written in grams. In grams. That's the difference. And for practical purpose, we prefer molar mass because we can manipulate molar mass. We can manipulate grams. We can't manipulate AMU. AMU is pretty much theoretical value. Theoretical values. You need to have a special instrument to operate AMU. But grams, we can do grams, uploading balance anywhere. We have a scale. We can do 20 grams of water. We can do 18 grams of water. We don't have any problem. We can do 12 grams of carbon. Is 1 mole. So 1 mole of carbon equals 12 grams. So if you have 0.11 gram, how many moles you have? Put 1 mole here over 12 grams. Again, I'm looking for mole, so mole has to be on the top. So I do the calculation. I can use my calculator, my cell phone, whatever. Okay? So 0.11 times 1 divided by 12. That gives me
0.009.
0.009. What's the unit? Moles. Should be moles. Moles of carbon. Okay, so the first one is answer how many moles you have. How many moles of carbon atoms in 0.55 carats? I have 0.009 moles of carbon. That's what I have. Okay? Now, there's a follow-up question. The follow-up question is that how many carbon atoms are in 0.55 carats? It's the same question. Yeah, it's the same question, pretty much. But the point is, over here, how many moles? Over here, how many carbon atoms? See? Don't get confused with that. Whenever, how many atoms? What comes to your mind? It always comes Avogadro's number. Avogadro's number. How many atoms? How many molecules? How many particles? If you see that word, how many atoms, how many molecules, or how many particles, then it has to be related with Avogadro's number, which is 1 mole of anything is always 6.02 times 10 to the power of 27. 1 mole of anything. Just like 1 dozen is 12. 1 dozen egg, 1 dozen pencil, 1 dozen of anything. As far as it is dozen, it's a dozen, it is 12, right? By that definition, by that principle, 1 mole of carbon also has 6.02 times 10 to the power of 23 atoms of particles in 1 mole. So if I have 0.009 mole, how many carbon atoms I have? Then I'm going to multiply that by 6.02 times 10 to the power of 27. Okay, so So for the second one, for the B, moles of carbon. Okay. How many carbon atoms? So I have to break the relationship between 1 mole of carbon has 6.02 times 10 to the power of 23 atoms of carbon in 1 mole. So if I have 0.009 mole of carbon, I'm having X number of atoms. What's your expectation? Is it less or is it more?
Less.
It's going to be less, right? Because 1 mole, 0.009, is a little bit less than 1, right? So it's going to be less, but to get the accurate number, we multiply, yes. Times, always, the desired limit has to be on the top, okay? Over 1 mole. That's the setup, okay? And you know, if you have the right setup, you always see that the unwanted units will be eliminated anyway. The unwanted units will be eliminated. Eventually, they will be eliminated, and the desired unit stays there. Okay. So what you can do now, most of you got confused with 10 to the power of 23. Please don't ever get confused with 10 to the power of 23. Forget 10 to the power of 23. Just multiply 6.02 times 0.009. Okay? Okay, and then we can leave this as is. That's not really a big issue here.
But when you use calculator, the value is going to change. The power is going to change.
That's fine.
Okay.
That's fine. Now, what is that you multiply? 6.02 times 0.009. Will be what you get.
5.5.
5.5.
5.5.
5.5 times 10 to the power of 21. Okay, that's what the calculator display shows you.
I got 5.418.
I used instead of what? 5.418
418.
times. Well, I wanted just to know.
Yeah, it's 21.
It's what the calculator display
Yeah.
shows you. Okay.
If you just multiply 0.009 by 6.02, you get 0.54.
Yes, that's what I would like to get. What's that you get? If you just multiply these two, what's that you get?
0.5418.
0.5418
5418.
times 10 to the power of 23. You may get this. Okay, you may get this. This is I think the first step. When you just multiply 0.09 by 6.02, most of the calculator display might have been shown you unless you have anything like technical or upgraded, but you get this, right? Now, you can leave this as is, it's okay. You can leave this as is, or you may say maybe 0.5418 or 0.05.
0.54, exactly like that.
Like this.
0.05.
It should be 0.5. 0.05.
I got 0.
Okay, it should be 0.05.
0.05.
It's 0.05.
Yeah. Get it, man.
Okay, all right, okay. 0.05. This is what you got, right? Now, one of the reasons is that we can leave it as is, but the best way to rewrite this, maybe you have to move the decimal point at least 2 units to the right. The reason why this number is always called the coefficient, like I said, exponent. The coefficients are a number that has to be between 1 and 10. I mean 1 and 9. It's more preferable to put it like this. Okay, so So if you move the decimal point 2 units to the right, okay, it's going to be like 5.418. You know, when you move numbers like this, the decimal point to the right, it's going to be the power, 10 to the power of minus 2. When you move the decimal point to the right, okay, it's going to be negative 2 units because that's why I have 2, but it should be minus, okay? And times 10 to the power of 20. Now because the same base, the exponents has to be added. That's the rule, that's the mathematical rule. So I think that's how you come up with 5.418 times 10 to the power of 21, 21 carbon atoms. Is that carbon, right?
Yeah.
Carbon atoms.
I'm sorry, which one's more preferable, like the first one or is that?
Yeah, it doesn't matter, but this is more preferable. You're asking the second one,
Bottom.
the bottom one. The bottom one is more preferable. Okay, the bottom one is more preferable. If you have this, this is an answer. Okay, nobody would say it's wrong. It's an answer, but mathematically, this is more preferable. Yes.
And instead of taking the 0.009, the number of moles, okay.
Yes.
So, can we add some more ranges after 9 so that
Like what?
0.0091
91.
166. I mean 166.
Oh, is this what you got when you do the calculation?
Yeah.
Okay, okay. So yeah, we can do that, and
It changed a little bit, like it's going to be like 5.52 times 10 to the power of 3.
21. Right?
5.5
Yeah, it's gonna change.
times 10 to the power of 3.
21. Okay, as far as it's 21, it's not a big problem really, but it's still the power of 21.
The first
Is
one's
what we're
really
looking for.
I got 5.5 too, so it's like 5.1.
My question is that how, after the decimal point, how
So how many
I
decimal
want to
places
do
we
this.
go? You always have to go with the original numbers, with the original problems. Let's say, for example, the original problems has 2 significant figures, right? 0.55. I would stick with 2 significant figures. Maybe I can add 0.0091 and remove this, because this is 2 significant figures.
it was like 66. Actually, for that
0.166, then you can just say 0.0092. 0.0092.
Why do you do it? Why do you do like questions? You have to change it like every time you got an answer. Like every time you got something, you have to change all the change the sign of the function.
Well, here is my, not rule, but like as a basic principle, you have to go with the original problem. Go back with the original problem. The original problem has how many significant figures? Whatever steps you go, and always the final answer, like let's say how many carbon atoms are 0.009, I would say 0.0092 because I have it was given to me
So if
0.55.
you got like 2 steps, you have to change for the first step you change to like 2, and then second step you change to 2 again.
Yeah, keeps that too. Yes. Okay. Okay, but you know, on the test, I'm not going to give you like a choice very much closer to each other. Okay, I'm not going. By the way, I'm not going to give you 0.05418 times 10 to the power of 23, and at the same time, don't expect me to give you this. Okay, because numerically, some of you came up with this answer. Some of you came up with this answer. I know this is more preferable, but I don't want to give you like confusions in numbers. That's not the issue here. The issue is, do you understand the principle? Do you understand the principle? How to solve the equation?
But if we use different number of significant figures, we're going to get a different answer from what we put as the answer in the.
Well, on the test, you know, you have to go with in accordance with the number of significant figures with the original value. So in this case, for example, instead of calculating 0.009, we may calculate something with 0.0092. So the number of atoms that you get from 0.0092, that will be the final answer.
Because we started with 0.5.
Because we start with 0.55. Yes. Because we start with two significant figures. Okay? Okay. Here, calculate the mass in kilograms of 219.9 moles of boron. Okay. Now, things are getting a little bit heavy. I mean, heavy means like huge amount in terms of the amount. It's heavy. 219.9, you have to calculate the mass in kilograms of this much more. So, what is the approach here? Let's say that you're doing this problem right now at this point. What's the first thing that you need to do? You have to pick what's this element? Boron, right? We need to find what? The atomic mass of boron. The atomic mass of boron. And you have to look on the periodic table. Okay, you don't have to memorize this. You have to look on the periodic table, or this information will be given to you. So what is boron equals to? 10.8. That is, so if I want to write 1 mole of boron, how do I write that?
11 grams.
Grams. Okay, 10.8. Okay, 11. That's fine.
But it's going to be a gram.
It's going to be a gram. That's the point. That's the important thing. It's going to be a gram. That's 1 mole. It's going to be a gram because it's molar mass.
I have a question.
Yeah.
So should we use the approximate value or the exact value?
I would prefer whatever is given to you. Okay. Like for example, on the test, it's given 10.8. Use 10.8. If it's given 11 grams, use 11 grams, depending on what's given to you. Okay. These are average weights anyway. Okay, average weight. It's not like exactly, it's not like accurate. 10.8 or 11. Those weights are applicable here. So let's go with 10.8. Or to make it easy, let's go with 11. 11. So 1 mole of boron is 11 grams, right? Okay. So if 1 mole of boron is 11 grams, then I have 290.9 moles of boron. How many grams are there?
23.7.
How do you do this? How do you operate this? You multiply. So everybody's clear with that?
How did you get rid of that?
It was from the periodic table. It was from the periodic table. Okay, you just
So you
look
just
for
round it off?
on the periodic table. It says 10
Boron
point.
is 10.8.
Oh, okay, we picked 11. 10.8 and 11. They are very much closer. If you don't like to round them up, you can say 10.8. It's not a problem, right? The point is, how many moles? I mean, how many grams we have in 219.9 moles? What do you do?
19 times 11.
Yes, 219.9 times 11. Okay. So if you multiply, you got a number. You say that was
2418.9.
2,418.9.
2,418.9.
Okay, he picks 11 actually.
You said choose to what?
Yeah, well, we pick 11. Okay. Okay. To get the same answer, let's pick 1 mole of boron is 11 grams. Okay. Let's pick 1 mole of boron is 11 grams.
I'm sorry, what answer did they get?
Depending on what you have, Beverly. Do you have 11 grams or 10.8 grams?
11.
Okay, if you have 11 grams, how many moles are there in 219.9? Multiply 219.9 by 11, right? So what you get? You will get 2418.9. That's what you get. And what's the unit? It's grams. It's grams, right? Now, the point is here, you have to change into kilograms. Okay? Yes, how do you do that?
1 gram is like
1 kilogram
1 gram.
equals to 1,000 grams. Now, 1 kilogram equals 1,000 grams. So, if you want to change 2,480.9 grams to kilogram, what do? You divide by 1,000. You divide by 1,000. So you ended up with what?
2.418.
Yes, 2.418, 0.9 kilograms. Kilograms. Do you understand the principle? That's my point. Do you understand the principle? Does that make sense? Okay. Now, see, sometimes, because names are.
So when the test, you're gonna get all that?
What do you mean all that? The units, like the atomic weights, yeah, will be given. The only thing I need is that every information you don't have to memorize, okay? But it is important for you how do you operate the problem, okay? How to change from mole to mass, how to change from mass to mole. What conversion factor you're going to use. That's something that I'm not going to ask you to remember 1 mole of boron or 1 mole of carbon. That will be given to you. 1 mole of boron is 11 grams, or 1 mole of carbon is 12 grams. Okay, this will be given to you. But how to manipulate that is something that you have to do it. Okay. So again, I want you to go back with the strategies. Okay, analyze the problem, write down all the informations, break up what is known and what's unknown, find relationship between the known and the unknown values. These are really important steps. If you think everything has to be related with that. For example here, what is the mass in kilograms of 8.8 times 10 to the power of 4 moles of tetraphosphorus heptoxide? Tetraphosphorus heptoxide. Okay, what are important key figures here? What's that we need to know?
Molar mass.
The molar mass of this compound, tetraphosphorus heptoxide. You see, we have to go back with chapter 2. We have to go back with names. See, names, you can't ignore names. You can't skip names. Always names have to be applied. Tetraphosphorus heptoxide. Don't expect to write the chemical formula sometimes. So what is tetraphosphorus heptoxide looks like? What is the chemical formula?
P5O7. P5O7.
P407.
P4O7. Tetra. P4O7. Tetra is 4. We have to go back with the names. Tetraphosphorus hept is 7. Heptagon. Hept. You see, you have to, when you're going to get time, you have to go back and review those terminologies. So this is a key. Tetraphosphorus heptoxide. That's one key. Okay. So what do you think you would do first?
Calculate the mass.
The molar mass. Calculate the molar mass of what? Tetraphosphorus heptoxide. What is the formula for tetraphosphorus heptoxide? P4O7. So what is 1 mole of tetraphosphorus heptoxide will be equal to? I can tell you, phosphorus has 31, and oxygen has 16. 236. Okay? Anybody have 236? Any witness?
Yeah.
Yes? Okay, 236. 236? Okay, 3 people got 236, right? That's 1 mole of tetraphosphorus heptoxide equals 236 grams. How do we get that? 4 times 31 plus 7 times 16. So that's 1 mole. That's 1 mole, remember. And what the unit should be? Grams. There's 1 mole. If it's molar mass, the unit has to be in grams every time. Now, if we have 8.80 times 10 to the power of 4 moles, how many grams is it? 1 mole has how many grams? 236, right? 1 mole has 236. So if you have 8.8 times 10 to the power of 4 moles, how many grams it should be? A lot. You multiply. 8.8 times 10 to the power of 4 times what? 236. Right? Because 1 mole has 236 grams. If I have 8.8 times 10 to the power of 4 moles, it's going to be multiply 236 by 8.8 times 10 to the power of 4. So that gives me a huge amount of grams.
2.0. 0.0768000 times 10 to the 7th.
It's going to be what? Okay, let me write this down. If you multiply 8.80 times 10 to the power of 4 mole, 236 grams over 1 mole, you get what?
2.0768 times 10 to the 7th power.
10 to 7
Yeah, correct.
grams. It's a huge number. Okay? So, but the good thing is we have to change this into what? Into kilograms. So we have to divide this by what?
1,000.
By 1,000. Okay? Divide this by 1,000. So what do you get?
2.0768 times 10 to the 4.
10 to the 4.
0768 times 10 to the power of 4 kilograms. Kilograms. Okay, we're going to continue. We have 5 minutes left.
Yeah.
We have 5 minutes. What things can I do? Okay. Okay. Let me explain a little bit about empirical formula and molecular formula, just to refresh your memories. What's the difference between empirical and molecular formula? Empirical formula always tells you the simplest atoms, the relative number of atoms in a molecule, whereas molecular formula gives you the exact or the actual number of atoms, right? That's the theoretical perspective, but we didn't learn, or explain how we can calculate empirical formula or how we can calculate molecular formula. That we didn't do so far. These are the important steps I want you to follow here. These are the important steps for calculating the empirical formula. Sometimes, when you do analysis, the percentage, it's given, like, for example, I would say, I have a sample of sample. That sample has 20% of iron and 75% of chlorine. That's the quantitative result, right? Based on this, how do we calculate the empirical formula? What is the formula? Okay, I have 20% of iron, 70% of chlorine, or 1% maybe oxygen, and make it together 100%. From that data, we are trying to figure out what the empirical formula looks like. Okay, so these are the steps that you need to follow. Whatever amount is given, sometimes it's given in grams, sometimes it's given in percent, it doesn't matter. We have to change into moles. You have to calculate the moles of each element. Then the next step is going to be divide each of the mole amounts by the smallest number of moles. Once you got the mole ratio, you have two ratios. Pick the smallest one, pick the smallest mole ratio, and then divide each mole by the smallest mole ratio. By the smallest mole ratio. Because we're talking about empirical formula. We're talking about the smallest whole number ratio. So we have to divide by the smallest number. And obtain the set of whole numbers and write the subscripts for the empirical formula. Once you get, after you divide, try to have a whole number. Okay? It's not by force. It's not like by twisting the arms, but try to have a whole number if possible. And these whole numbers are used to write the empirical formula. Now the question is, how about if I don't have whole number? Okay? How about if you have whole number? There is situations that you're going to round, approximate. There is a situation that you can't round. Okay? We're going to discuss about that. So I want you to read these examples. Okay? These examples here, how to calculate the empirical formula. And I want you to calculate for Friday. I want you to try these examples. Okay, so I will explain this in